Thank you for kind introduction. So, second session is about generative models for mobility. So again, in this session, I try to incorporate some high-level overview of generative models. So I believe some of you already have used generative model, like a diffusion model or GAN-based approaches, but who has like in-depth knowledges. Hope that anyway you enjoy my talks. So agenda for the second session includes generative AI and also application in specialized domains, and ended up with the challenges and research opportunities. So in our lab, we are extensively working on medical related analysis. So I will try to introduce how generative AI can be used in medical imaging application as well. So from AI to generative AI, so I think some people or some students already have used state-of-art generative AI like diffusion model and some image generation tool, which gives you very high quality of image output. And also LMM would be one of generative AI method. So in terms of text generation, Llama variants are one of the representative one. And also for image generation, diffusion, sorry for the typo there, diffusion-based model such as ControlNet. Basically, you are inputting some prompt so that you are controlling those generation output. And stable diffusion model works pretty well to obtain high quality of generation output. And you can use this generative AI in multiple applications. So when you are generating some synthetic images in different type of application, this Gen AI has been used extensively. So for example, if you try to generate images that has a privacy issue, you can use this stable diffusion type of approaches to generate images. And that's basic concept of generative AI, but let's start with the difference between supervised learning and unsupervised learning. So for those who has used AI, you may know this concept and differences as well. So when you are working on supervised learning, you would have a data set, which is the input data, and also you would have labeled output annotation. And objective is to learn a function F to map input to output. And common application involve image classification and some regression tasks or object detection and even image captioning as well. And unsupervised learning, meanwhile, you have a data but no label provided. And objective here is to discover the underlying structure of the data and try to learn patterns and grouping and distribution as well. So common application would be some clustering, including k-means and dbScan, and also dimensionality reduction and also density estimation would be some application. And people are using self-supervised learning extensively, which was pretty fine. And when you are using foundation model, this self-supervised learning, which is under umbrella of unsupervised learning, has been used extensively. So in generative modeling, so first of all, given training data, the goal is to model how the data was generative by learning its probability distribution. So first, you estimate the probability distribution, which is P model X, that could have generated data, and you try to sample new data set, X, from this learned distribution. And this is a basic concept of generative modeling. And there are key ways of solving this problem. One is explicit density estimation. So basically the model explicitly defines and computes the probability distribution, P P model X. And another way of approaching this problem is implicit density estimation. So the model learns to generate samples from Px without directly defining the distribution. So why people are using generative AI again? So you try to, or you are interested in generating realistic samples to augment and diversify training data set. So what if you have a limited data set? People may use public data set available, but typically when you are solving some specific downstream task, you would not have a sufficient label, like realistic data set you can use. So that's why you try to use generative realistic samples by using this generative modeling. And also you can enhance data quality. And as I said, these days, generated images from diffusion model produce really high quality output. And you can learn meaningful representation and extract some insights and also model the physical world. And generative model has been popular these days so far. And this is a quite popular table that gives category of generative models. So as I mentioned, there are two ways of solving this problem by approaching explicit density estimation, and the other is implicit density. So there are old methods under this explicit density estimation, such as pixel RNN, CNN. Those are one of tractable density estimation method. And in this explicit density estimation method, variation autoencoder is also one of representative method. And under implicit density estimation, GAN-based approaches would be the one under this category. So what is it like building a generative model? So consider that our data is composed of 1D points. So for example, 1D data is distributed according to uniform distribution. So once we know this underlying function that produces data, we can create a new sample based on this function we have. And the second example, so data is distributed according to 1D Gaussian distribution. So once you have this probability this function, so once you are aware of the data distribution, you can just sample new data set based on this defined function. So what is it like building a generative model? So if you know the ground truth distribution, so in the first example, I talked about uniform distribution, and the second one was about a Gaussian distribution. So once you have this understanding, you can generate a new sample of one data by sampling from the distribution. And since the ground truth distribution typically is unknown, we try to use neural network to approximate the distribution. So due to large scale of the data set, and also you may have seen deep generative models has been powerful in this generative AI field. And this is basically to learn a model that its output follows the true data distribution. So on the right figure, it gives the example of true image, which is X, and people are interested in getting generative images from G based on the generative models. So I will skip introduction of like GAN-based method and some variants of GAN method. Like people may already have used cycle GAN or style GAN. So basically this is an example from big GAN and also style GAN and other GAN variants. But this 2025, their quality has been improved pretty much a lot, significantly, because of the scale and also data set available. And I'm not sure how many people have used diffusion model or stable diffusion based software tool. Their quality output is pretty outstanding. And especially, I'm not sure how many people have used Google VO version 3 that gives video generation and also cleaning. Their quality has been significant. But common to all these models, deep generative models, is the use of attention layer. I talked about transformer model a lot in previous session, But in this session, I would like to go in depth about this transformer, just because this model is the common thing that has been used in generative AI field these days. So importance of transformer in modern AI research and application, as I mentioned in previous session, multi-domain integration. Basically, you are using multiple data input source, and flexible and scalable architecture would be characteristic. And in vision field, typically they have achieved superior performance in different downstream tasks. And also you can achieve deep contextual understanding. And this is a pathway to generative AI. So I will go in depth about this transformer so that you can have better understanding. For those who already understand the transformer architecture, sorry about that, but let me go through this concept again. So let's talk about transformer. Neural network, this is based on attention. So previously, people have used recurrent neural network and also recurrent layers, but now you are using attention module in this transformer architecture. So this transformer model processes entire sequences in parallel, which boosts speed and efficiency. And this architecture achieves highly scalable with the increased computational power and data size, which should be limitation, but anyway, this is one of characteristic. And they have two parts. One is encoder and also decoder part. So main component of block, they have a self-attention and also layer normalization and some feed-forward neural network. And they have a positional encoding, which is quite important in vision tasks. So these are summary of encoder decoders of transformer architecture. So encoder part, you try to produce context from input and you generate a representation encoding the entire input sequences. And in encoder part, you have self-attention and layer normalization, and as I mentioned, feed-forward neural network. And decoder part would be the one that you are producing output that combines encoder output and previous decoder outputs to predict next token in sequences. So basically, they have a similar component, but they have an additional layer for outputs of decoder. And let's talk about tokenization, which would be a key important part in transformer model. So what is tokenization? So it converts text into smaller units, such as a word or sub-words or character. And tokens are mapped to numeric IDs. And why tokenization matters in this approach? Because it enables transformer to process consistent numeric inputs. And there are many algorithms that you can achieve this tokenizer, such as word piece from BRT and PE from GPT model. And for example, when you have word unbelievable, so you can make each component, which is token, such as like UN, on, and believe, and able, and you can map it to numeric IDs, as you can see. And next step after tokenization, once text is tokenized into IDs, each token is mapped to a high-dimensional vector called embedding. We talked about embedding frequently, and this is what you get after tokenization. And why it matters? Because embedding gives numeric IDs, semantic meaning, which captures relations, similarity, and context. So let's compare token and embedding. So token ID would be integer, discrete integer, but embedding would be dense vector from that specific discrete integer. And I mentioned that this transformer architecture has a positional embedding, which is a very critical in vision field. And the role of this positional encoding is that this enables sequence recognition by providing unique positional signals. You don't have to know the details of this sinusoidal or cosine function, but to give you like concept of this positional encoding. So once you have this input images, vision transformer try to use this positional encoding so that you can recognize some of indexes. So first of all, you make these images into patches and somehow you have to understand the location of image patches, and positional encoding is the one that recognizes each specific ID or location. So this is how you play with this positional encoding in vision transformer. And key important part in transformer would be definitely self-attention mechanism. And this mechanism allows each position in the decoder to attend to all positions in the decoder of previous layers. And briefly speaking, self-attention computes a weighted sum of all input representation with respect to their relevance. So benefit of self-attention is that it allows the model to dynamically focus on different parts of the sequences. So in terms of object recognition or scene understanding, this self-attention is pretty valuable because you can dynamically focus on different parts of the sequences, which would be a key information when you are getting recognition output. And it also facilitates parallel processing, unlike RNN, which has been used previously. And with that, process data sequentially. So if you see the images in the right side, what if you have an input, you will get the attention map, as you can see, that focus on different part. And this concept has been explained a lot in language model, but these days we are working on vision language model, and also vision transformer is the one that we are actively using. So this self-attention mechanism helps to have a better global understanding and also localization problem. And they have a query key value, and each token is transformed into 3 vectors. One is query, and basically what this token is looking for, and key, how relevant this token is to others, and value, the information this token carries. And how they work together, each token's query is matched with all keys via a dot product, and scores are scaled and passed through softmax, and then you are getting attention weights. And these weights are applied to values, and what you are getting is weighted sum. That would be the output of the tokens. By doing so, this allows each word or your input to attend to other dynamically and capturing context across positions. So when you are working on a scene understanding, you may require a global understanding because you don't want to focus on just local area. When you're using convolution neural network, you are more focusing on specific area, but transformer, by approaching this problem, you will try to solve this problem in holistic way, so you have better global understanding in images. So attention in transformers, they have scale dot product attention, and in the previous session, I talked about multi-head attention. So they have a self-attention and cross-attention all together in this attention block. And these are summary of self-attention in transformer. So they have a query key values vectors and also attention score. And you would have weighted sum in the end. So again, transformer has a encoder and decoder part, and encoder would be representation part. So basically, what if you have an input, you try to have a context from the input, and the decoder part would be for generation. So again, encoder, the role is to have representation, and input would be entire input sequences, and decoder part, the input would be encoded embedding along with partially generated sequences. And output from encoder is contextual embeddings of input, and output of decoder would be next token prediction or entire output sequences. So that's why this is for generation part. So transformer, due to this characteristic, has been used many applications in generative AI, not only GPT, but also BERT and also DALL-E and other code generation using LLM. they are extensively using transformer approaches. So in stable diffusion, which is one of representative method, they are using UNet type of architecture, and this UNet architecture is used in stable diffusion to denoise latent features, and it combines residual blocks and convolution layers and attention mechanism. And as you can see in the third block, they have a self-attention which captures internal structure, while cross-attention in orange color, they inject text guidance. So they have a cross-attention layers, and this cross-attention links image features to text embedding, and text token here serves as keys and values, while images pixels act as queries. And this mechanism ensure generated images align with the texture description. So this cross-attention layer is pretty valuable when you are working on alignment. And cross-attention layer, they try to project image features into queries and text embedding into keys and values. And this model learns where each word, such as kitten and puppy or bear in this case, should influence the visual output through attention weights. So as you can see, they have it could be word or it could be sentences, and this cross-attention layer try to focus on specific word in that input texture embeddings. And self-attention layer, image features are projected in queries, keys and values, and attention map is computed via this QT to the T and applies to values to produce enhanced feature map. And this mechanism enables global reasoning within the images. And they allow each pixels, which is query, to attend to every other pixel that is key within the images. And this generate a spatial attention map, as you can see in this slide, that can capture long-range dependency. So that's why you can have a global understanding due to this characteristic. And this enhances understanding of object structure and context. And next, I will talk about some semantics in attention feature, which is quite important in transformer model. So there are many papers published recently try to utilize this attention map for image generation, especially using diffusion models. So these are example of image generation using text prompt. So what if you see the top figure, and let's assume that you have an input image with a cake, and you can inject a text prompt with a different type of noun, such as chocolate cake or bit cake and pasta cake as well. But key thing is that people are interested in maintaining some structure. So if you see the bottom side, they are maintaining a structure of target object, but somehow they are achieving image or style transfer. So the top one is manipulating object in the different object, but the bottom one, basically you maintain the structure of input, but somehow you achieved style transfer. So some of you may have used a cycle again to achieve image transfer or style transfer, but also you can use this text prompt-based approaches to achieve this image or style transfer. So here, this is a key concept behind it, how you can have this style transfer. And ControlNet is one of representative one, so that you can inject some text or text embedding into attention map, so that you can have a robust or better generation output. So these are some of the example from recent paper, and let's take a look at the images on the top right one, the text prompt would be photo of cat riding on a bicycle. That is an initial prompt. So if you edit it with another word, so basically you replace that word bicycle with a car, and the output you are generating would be this different image like a style, or you can manipulate the object by injecting some text prompt. And another recent paper to achieve style transfer, they try to use cross attention map. So motivation here is, what if you have two different sets or unpaired images? Are you able to generate images with a different style? So cycle GAN method was a way to solve this problem. So what if you have an unpaired data set? You can achieve image or style transfer. But if you use cross attention mechanism, this is also available. So let's say you have these two different animal input images, and what if you're using attention? You can identify some of the key components within these images. For example, you can focus on like a head or different legs in two different sets of images. And by using this attention module and also cross image attention, you can have corresponding points. And this cross image attention is valuable because they try to align features from different images, as you can see in the top and the bottom side. And queries, keys, and values are projected separately for each images, which enables the model to relate corresponding region across inputs. So if you see these images with one another, basically cross-image attention can focus on the same area. So you can focus on head part in giraffe and also zebra. And this cross-image attention makes you have a paired or better image style transfer. So graphic conference like CGraph, many people are working on this image translation techniques, and this performance has been significantly improved these days using diffusion model and also control net based approaches. And those are like high level of overview of generative AI method. And I will talk about some application in specialized domains. And in mobility application, people also are interested in generative model because this is one of recent review paper that I found, and people are interested in using Gen AI in multi-agent human trajectory prediction. So why people are interested in using generative models in mobility application? And traditional method outputs a single deterministic trajectory, but human and vehicle behavior are inherently uncertain and multimodal. So again, traditional method is producing single deterministic trajectory, but Gen AI is available to output multiple diverse plausible futures and capture distribution over future path. So this is relatively old work, but some people or researchers were interested in using GAN-based method to produce some trajectory of pedestrians. So they have used some LSTM and also GAN-based method. But when I searched some relevant paper, people try to use generative model to produce some trajectory of pedestrian or movement of vehicle in first-person view image data set. These are some methods that I found in mobility application, but I'm also working on medical imaging application. So let me briefly introduce some Gen AI application in medical field. So this is one of project that I did when I was postdoc research fellow, and objective this study was to develop a solution for creation of pseudo-CT images of upper abdomen from MR images. So this project was sponsored by GE Healthcare, and they were interested in generating pseudo-CT images. And because you can use CT images and MR images at the same time to have a better understanding of anatomical features. But anyway, there is a time cost, and also you have to use both modality at the same time to collect such a data. But they were interested in relying just single modality and try to produce CT or pseudo CT images. And to solve this problem, we try to develop pseudo CT from MR, which can help offer MR only radiation therapy planning solution to radiation oncologists. So I have received MR images with different sequencing, and also I have received corresponding CT images. So as you can see, they have a different image characteristic, and CT images definitely you can see some hard tissue like a bone area. So initially I have used cycle GAN, which is a kind of old-fashioned method, just because there was a literature for brain pseudo CT image generation using a cycle GAN. But in my project, the image resolution was higher than that, and also this was a 3D voxel images. So just adopting 3D cycle GAN was challenging. So in my project, I try to make a slice or image sequences and try to deploy or apply a 2D cycle GAN separately and then combine them all together. So these are some of the examples that I produced. Left column shows real CT images, and the very right column shows corresponding MR images, and the center one gives generated CT images. So if you see a white feature that is a saturated pixel area, that is a bone area. So it's not perfectly generated some of the critical features, but still I was able to get pseudo CT images. And to improve the quality, since cycle GAN is more about global translation, we can include some attention-based improvements so that you can have local focus as well. So if you are using cycle GAN with attention-based improvement, definitely you would produce some better quality of output. And since I'm the person focusing on image analysis, super resolution is another good example. So I'm also working on this endoscopic medical image data set, and typically their image quality is not very outstanding because you are inputting this imaging system in the human body, and they have an image blur, like motion blur, and sometimes there are smoky effect and also haze effect as well. So to have a better quality of input images, image super resolution technique would be a way to solve it. And previously, conventional method is just about interpolation techniques. So you can use different type of interpolation techniques so that you can have a better texture generation. But deep learning method is also very powerful technique due to large scale of data set. You can have a better texture generation, better texture, and also sharpening effect as well. So in my research, I try to develop an architecture that incorporate discrete cosine transform, where you can get the low frequency component and high frequency component separately. And then you try to have two different paths so that you can learn you can have an understanding of low frequency component perspective and also high frequency component as well. Because low frequency component has low frequency component is for general image understanding, like a color information and also some contextual information. But high frequency component is for edge area or sharpening effect. So that's why we have two different paths so that we can have a better super resolution output. So I have used this type of endoscopic image data set, and this is low quality. The center one is low quality of images, and if we are using deep learning-based super resolution technique, I'm not sure how you can see this area, but these vessels has been generated with a better delineation. They have a better sharpening and also better texture. And this super resolution technique can be adopted or applied in mobility systems as well. So if you are using this technique for autonomous driving, so you can have a better resolution so that you can recognize license in a better way. And also if you are using UAV images like drone surveillance, you can have a you have a high quality of images so that you can recognize targets in an easily manner. And super resolution is one good example for generative AI. And also vision language model would be also interesting topic in Gen AI field. So this is our recent work. Again, this is about medical domain. And our lab was working on endoscopic image understanding. So what if you have this type of videos and user or clinician can ask about these scenes. So sometimes residency, which is like novice clinician, would not have a deep understanding of these videos. So what if clinician asks some question about this surgical scene? The output that we are getting would be description of surgical video. And our work was focusing on current surgical scenario and also future surgical actions as well. So we curated our own data set focusing on past, current, and future surgical action. So we curated our own endoscopic data set and also try to have our own model so that the output we are getting would be like scene description for clinician. So this is a collaborative work with Johns Hopkins, and they had a clinician who has in-depth knowledge about this endoscopic data, and they pretty much valued what we have done. So hopefully we can release this paper in the near future. And vision language or generative AI application in mobility, definitely there are many ways to incorporate it, like scene understanding and captioning or reasoning. So what if you have this first-person road view? You would have like traffic light, or you can see some object, for example, and then you can use this vision language model so that you can have a better reasoning. Because in mobility system, you should have a better contextual understanding, right? So I think this vision language model would be very valuable in different mobility application as well. And so those are some specialized domain or application. And let's talk about some challenges and research opportunity. So again, since in mobility application, real-time inference would be very valuable and people are very interested in. And also multimodal grounding that improves alignment between language, vision, and spatial context would be a key thing that you would like to solve. And rare event generation would be a very interesting topic because people are interested in generating images because sometimes they have a limited labels or data set. And rare event generation would be a very interesting topic, especially in my domain, like surgical procedure. There is a limitation of getting like some rare event, such as like bleeding effect. There are not, you cannot get the public data set with that certain rare scenarios. But if you are using this Gen AI, you can somehow generate high quality of data set that can be fit into the model as a training data set. And generalization, so if you have images in different scenarios that can help your generalization. And these people are actually working on multi-agent modeling and also perception action integration, as I mentioned in the previous session. So these are some of the potential way to work on as a research problem, and also sensor robustness to use generative prior to recover from occlusion noises or adversary corruption would be some interesting domain. So thanks for the attention. And this is pretty much I prepare regarding Gen AI. And I try to explain some key concept in high level and try to introduce some specialized application. But if you have question, I'll be happy to answer after this presentation as well. So again, thank you.